Hello everyone, welcome to the numerical methods class. In this class we will be studying chapter 11, and in this chapter we will be studying the special matrices and also the Gauss-Seidel approach to be able to solve the sets of equations. There are some special matrices we are going to introduce in this course, and these are the banded matrix and symmetric matrices. We will be talking about the solution of these. The banded matrix is a square matrix that has all elements equal to 0, with the exception of a band centered on the main diagonal. On the right hand side here you can see a banded matrix. Actually we have a diagonal, and around the diagonal we have a lower and upper diagonal as well. This is, for instance, on a banded matrix, a three diagonal matrix it is called. And the bandwidth, which is the width of the starting from the second row to the last second row, you can measure the width as the number of terms, which is 3 here. This is a three diagonal matrix with 3 bandwidth. So basically the diagonal will have upper and lower diagonals as well, and the rest will be 0. This is called banded matrices. And for these, the pivoting may be unnecessary for solving, and there are some algorithms that we will show how to solve this. Another matrix is the symmetric matrix, and this is a square matrix where the aij and aji terms are equivalent for all I and j. Basically, the terms around the diagonal will be equal for ij and ji, the reverse of these. For example, a21 and a12 are equal, and a31 and a13 are equal, and also a32 and a23 are equal. So around the diagonal we will check, if we fold actually on the line of diagonal, the terms corresponding to each other will be equal. In that scenario, this is a symmetric matrix. So this is a 3 by 3 symmetric matrix, for instance. So for these two types of matrices, we have special solution techniques that we are going to show. For the banded matrices, we have a representation, as you can see on the right hand side, and basically we have a non-zero band, this band, and this band around diagonal, centered on the main diagonal, these are, and the rest are 0. So the first term actually have one less of the bandwidth, but starting from the second term we can measure the bandwidth. This BW is the number of non-zero terms in one row, starting from the second row actually. And half bandwidth is the number of non-zero terms after or before the diagonal term. So after or before this diagonal term there are equal number of terms, and if you measure it starting from the second row, it is called half bandwidth. And the bandwidth and half bandwidth has a relationship by 2 half bandwidths plus the diagonal plus 1. So bandwidth is equivalent to 2 half bandwidth plus 1. And also a banded system can be represented with this aij equals 0. So these are 0 if I minus j, the absolute value, is greater than half bandwidth. So we can mathematically define the banded matrix like this. And banded systems are frequently encountered in the engineering and scientific practices. They typically occur in the solution of differential equations. For instance, in the finite element analysis, finite element method, it is very common to see these kind of matrices. That's why solution of these is important. Also, other numerical methods such as cubic splines will involve the solution of banded systems as well. And the tridiagonal systems, the bandwidth equals 3, are the most common ones encountered in the banded matrices. We have a specific algorithm called Thomas algorithm to solve the tridiagonal systems, which means that a banded matrix with 3 bandwidth, as you can see here. And there is a special solution algorithm of this. It includes actually decomposition, forward substitution, and back substitution. So this is somehow a simplified version of the LU decomposition, and the algorithm is given here. For this, what we do is, first of all, we actually define each term as E, F, and G. So the first term doesn't have E because it has only 2 terms, for instance. E, F, and G. It starts with F, but the second term is starting from E, E2, F2, G2. Then the third one, E3, F3, G3. So basically the first diagonal will have E's, the middle diagonal will have F's, and the third diagonal over here, the terms will have G's. And in the end, we will have En, Fn, and G doesn't exist here. So when we define like this with these symbols, then we can use these pseudocodes, algorithms, to be able to solve this. Basically, in the decomposition section, what we do is we divide E's by Fk minus 1, then obtain the new E's. Then for Fk's, we actually multiply these E's by Gk minus 1 and subtract it from the Fk and find this. With this, we obtain the decomposition. Then we will implement forward substitution, in which we are going to use these constants, actually, the results. So the Rk will be calculated as Rk minus Ek times Rk minus 1. And after this, we will have back substitution, because eventually we will have a final term or final equation with one unknown only. So we will divide Rn by Fn, this Fn, because we will be eliminating this in here. And from here we will get Xn. Then we will start putting this into the other equations by implementing this formulation. And then we will obtain all the xk values. So let's work on this in an example to see how these algorithms work.